finite elements, still we're looking at finite element. What's really important here is knowing your boundary conditions as well as your stiffness matrix. Well, for hand calculation, the trouble there will be more on identifying or solving for the stiffness matrix, especially if the type of element that you're using is a plate or even higher, and then the assumption that you're having is quadratic or higher. Linear, in many cases, they're not allowed to bend. So if in case you want to use linear elements, you need to have more elements, or you have to increase the number of elements to be able to simulate the bending of your structure. Now let's have a look at this very simple derivation for the stiffness matrix as compared to what we have discussed last time. But we're going to review that again. And then I will present you of other ways of solving the stiffness matrix. So this is for a bar. What you simply do is to take the summation of forces of that one element and the summation forces of this second element. This one is in Moodle. I posted this one in your mechanics for Moodle. And then simply come up with equation, and you can come up with this F equal to A multiplied by U, and you have now this one as your stiffness matrix. Now this one is a very simple solution, but take note that this derivation is only applicable for bars. For other elements, this type of derivation won't work. You probably can use this one for springs. So springs and bars, you can use this one to be able to calculate for this stiffness matrix. Other than that, you cannot expand, or you cannot you cannot derive the other stiffness matrix for beams, plates, and so on to be able to get the stiffness matrix. Okay, so very simple, but only applicable for bars and springs. So again, this is what we have last time. I won't be going through this one because this one is just a simply summation of forces horizontal to be able to get your strong form, which is given by this equation. Right? So we have strong form, you have weak form, but finite elements actually rely on the weak form. So the method that we used last time was using the method of weighted residual, Galerkin's method. So what happened here, is that you have now here your finite element general equation. So you have your forces and displacement to be your boundary conditions. So your question is K. Now, assuming that you don't have any idea for that stiffness matrix K, what do? So you derive that equation, and there are many ways of solving this one. So for the bar element that we did, so we have your weak form, and this weak form, we use your method of weighted residual plus that Galerkin's method. So with this one here, we are able to derive your stiffness equal to the volume integral of B, E, D, transpose dV. Now, take note that B here will be your strain displacement matrix. And what is this b here? B here can be solved using your shape function, wherein your b is simply the derivative of that shape function with respect to x. So once you have this shape function, you will be able to derive this one here. The symbolic form for a bar, that is k minus k minus k and k. So the purpose of using the method of weighted residual is only to get this relationship here. That equation for your stiffness matrix. So you will be ending there. So to be able to get that symbolic form, or to be able to get a numerical value for k, so we know that this one is a matrix, but there will be some numbers in your matrix. So how do we derive that? Of course, you have now to use your, so k to this k. So how do we get that? From this to that. So there are many ways of doing this one. One example is what we showed, simply taking on the mapping, so trying to map. So here, what we do is, from here we have your mapping technique, wherein we have your, say, x1 to your C plane. So you have your x1, x2 plane, you bring it to C plane. And then the other one, before we will be able to derive the values, we introduce another term, which is your Jacobian. Of course, we also need here your shape function n. And after doing this process, once you get your n, you get your b, substitute in here, put in your Jacobian to be able to come up with this one. Now let's run through again that example. So we have now here your Now why am I doing this? This one will prepare you for that single chapter in your text or in your notes. So at least you have an understanding, you will be able to understand how to work on the problems there, because that is more complicated. So yes, we get this weight form, yeah, and then W is our weighting function, and we've also got our displacement interpolation function. By doing this one, we will be able to get N1, U1, and N2, U2. So after getting that displacement interpolation function, we have to have our shape function assumption. So take note that your shape function will always be 1 at the node of interest and others, and 0 for other nodes. So N1 at 1 is equal to 1 there, and N2 at 2 is equal to 1. So N1 at 2 is equal to 0, N2 at 1 is equal to 0. So take note of that simple definition of shape function. Now, this is just a very simple shape function, linear. And what does Galerkin method say? That so this is your weight form, wherein you have now your weights, or so-called weight function. So this weight function, according to Galerkin, will be equal to your shape function. So that here you will be able to get your strain displacement matrix values, which is dn dx. Now, all you have to do is just take the derivative of your N1 and N2, plug it to the weak form, and then simplify. So from here, what can we get from this one will be this equation only. Now please take note that this equation is only applicable for bar. It's different when it comes to beams. So there will be additional, well, just one term additional when it comes to beams here. So this one here. So that's what we were able to derive using the method of weighted residual and the Galerkin's method. Now, to be able to get the value of your stiffness matrix, so we want a symbolic form to be able to calculate the value. So we have the so-called mapping from your x1, x2 plane, or sorry, x1, x2 plane, and your Ca-C1, Ca-C2 plane. So in this case, just Ca-C at 1, Ca-C at 2. This one is basically Ca-C1, Ca-C1. So we have 1 and 2. So this one is mapping, but since we're just doing a linear solution, then we'll just take it as mapping from x-plane to Ca-C plane. So from this one, again, it's pretty much straightforward. Again, if you just really try, at least spend an effort to solve this one, then you will realize that this one is a very straightforward solution. Okay? And then here, we get now your sheaf function as a function of C, or Ca-C. So once you get that, you also get your strain displacement values. Put it here in this equation, but because your strain displacement now is a function of C, you need to have a Jacobian scale factor. So after that, once you have your sheaf functions here, you can simply substitute the values here, perform integration, and then you can get this value there. So as you can see, this one is symbolic form. We can only get symbolic forms for this bars, trusses, beams, frames. When you go to plates and higher order or higher elements, you won't be able to get this symbolic form anymore. You have to integrate numerically. And we will be doing that once we go through these different theories. Right. Let me present another form or another method . So this one now is a simpler one to be able to get the stiffness matrix of your bar. This one is called the direct stiffness method. Take note that this direct stiffness method can also be applicable to other elements. It's a lot simpler than the one shown in your notes, so I'm just going to show you. So why am I doing this one? Because there will be a lot of factors that your notes cannot really present. It's just a few pages, so a lot of information there have not been presented. So to be able to at least give you a background before you can solve those problems is to do a lot of this basic calculations or derivations, just to give you an idea. So let's look at the bar. Still, we're not going anywhere. We're still looking at the bar. Now, what happened here is that you must have a displacement function. So take note, we have been working on finite elements, so at least you know all of this. You probably don't have to memorize them already because you know them. So let's start with your displacement function. So another solution here is to assume the displacement function. If you want it to be linear, then that's simply equal to ax plus b, yeah? So what we're going to do here is to assume that your displacement is linear. So your displacement is a1 plus a2x, where a1 and a2 are numerical values or numerical coefficients. And x, of course, that will be your plane. So this is now your displacement. So what we can do here is, just to rewrite it, we can have this one to be 1 and x. So if you want to write it in a matrix form, so you can have here as A1 and A2. So again, this one now probably you should have known it already. So let's have a look at this bar here. There. So we have this one to be x equal to 0, assuming that this will be your length of the bar. And then you have this one to be x equal to L. So this one is from 0 to L. And of course, you will have, say for example, let's have, have node 1 and node 2. So node 1 and node 2, that is your node 2 there. So you will have a U1 and U2. So that's the thing at the moment. Now, our question here is we need to determine the coefficients here. So once we have this one, we will be able to get your shape function. So that's the purpose here. So once we know a function of u, we will be able to get your shape function, and then from there we will be able to get your stiffness matrix. So take note for a bar, this one is the volume integral of that B, E, B transpose dV. Or if you want to write it, again, rather integrating with respect to the volume, you integrate it with respect to the line. So this one now will be equal to B EA BT dx. So wherein, of course, we know that your dV is equal to A dx. So let's try now. So let's say that we have at x equal to 0. So we can now substitute these values to this one here. So we can have now u1 equal to, because that is at point 1, so u1 is equal to a1 plus a2 multiplied by 0. So this u1 is simply equal to a1. Yes? Now, moving on, at x equal to that length L, x equal to L, which is at point 2 here. So we can have now u2 equal to a1 plus a2 multiplied by L. So after this one, what happens, of course, we know that a1 is equal to u1, so we can have this one to be a1 a2L. So we have now here a1, that will be u1 plus a2L. Okay, quite straightforward. So you will have now a value for u1 and u2. So we can have now here a2 equal now to, let's solve for a2, that is now u2 minus u1 all over L. So we have now values for a1 and a2. So what we can do now is substitute to our displacement function. So once we have a1 and a2, we substitute it to your displacement function. So just a summary, your u is a1 plus a2x. Why did we have that? This is just an assumption, a linear assumption of your displacement. How did we derive that? No, we didn't derive that. It has been assumed. Who assumed that? We don't know. I mean, somebody has worked on this one and it works. So that's why we have this linear function. So that a1 is equal to u1, and then a2 is equal to u2 minus u1 all over L. So we substitute it now to our displacement function. So we can have now here u1 plus u2 minus u1 L x. How about that? So once you have that, once you have this one now, let's see what happens. You put those u1s and u2 together. u1 minus u1 Lx plus u2 all over Lx. Yes? We further simplify this one. Let's take away or move out u1. We have 1 minus x all over L u1 plus x all over L u2. Yeah? So after this one now can be rewritten in a matrix form. So you have 1 minus x all over L, and then you have here x all over L. That's your matrix, and then you have this one to be u1, u2. Or you can have this one, say for example, this will be n1, and this will be n2. That will be n1, n2, u1, u2. So again, you can look at this one again, u that is in matrix form. But if you want to just use that, you can also use n1 u1 plus n2 u2. So you are now able to get your shape function. So after getting your shape function, what's next? Once you have your shape function, what's next? Calculate for the... Anybody? So once you get your shape function, this one is your general guide. Your stiffness matrix. What is your stiffness matrix? This is equal to this one here. And this strain displacement matrix is what? D and dx. So once you have your n, your shape function, you can take its derivative with respect to x, so you will be able to get your strain displacement matrix. So once you get your strain displacement matrix, or strain displacement matrix, you can now calculate for your stiffness matrix. How about that? So once we get your n, we get your b. Once you get your b, you get your k, which is dE, dt, dV. So that's basically the procedure to be able to get your stiffness matrix. Once you get this one, depending on your assumption, so again, if you want to start this one, you come up with your displacement matrix or displacement function, solve your shape function, determine your strain displacement matrix, determine your stiffness matrix. So once you have that, then it will be straightforward now to calculate for your F equal to K multiplied by U. So let's have a look. So let's continue. What will be your shape function 1? So what is your shape function 1? Shape function 1. So shape function 1 is 1 minus x all over L. That first shape function. What about your second shape function? This one is x all over L. So let's try to test whether did we really get it right. You know that the definition of a shape function is that this one will be 1 at the node of interest, yes? And 0 at other nodes. So if, say, for example, for shape function 1, your x is equal to 0. So your n1 at 1 is equal to n1 at node 1 is equal to 1. Because x is equal to 0. n1 at 2, where x is equal to L, 1 minus L all over L, or 1 minus 1 is equal to 0. So n1 at 2 is 0. So let's have a look at this one here. n2 equal to x all over L. At x equal to 0, n2 is 0. At n2, or when x is equal to L, that is node 2, n2 is equal to L all over L equal to 1. So n2 at 2 equal to 1. So we tested out that this one is indeed a correct shape function. So you can have different shape functions. You can actually assume a quadratic and then test it out if you want to. Now let's move on and solve for your stiffness matrix. So we know that our B, so let's write our strain displacement matrix, 1 minus x all over L, and then this one is x all over L. So what are we doing now? So the thing is, once we have your shape function, you get your B. Let me put it here, B equal to the derivative with respect to x. So that is B, right? Your n is equal to 1 minus x all over L, x all over L. So let's try to determine your B matrix. What is your B matrix? First value, derivative of this one with respect to x. Value? What's the value of this one? Derivative of this with respect to x. Minus 1 all over L. What about this one? Derivative of x all over L with respect to x. Yes? So now, we can now solve for your stiffness matrix. That will be L there, or 0 to L. So this one now will be 1 all over L, 1 all over L. Let me bring out, so that is EA. Let me bring out EA. There. And then you multiply it with your minus 1 all over L, 1 all over L. This will be dx. So that is EA 0 to L. So what do we have here? 1 all over L squared. This one multiplied by that. Yes? So integrate individually. So if we integrate this one individually, what do we get? So this one is EA. What happened? x all over L squared yes, and if that is L, so this one is 1 all over L minus 1 all over L minus 1 all over L, 1 all over L. So then you can simplify this one too. Just right. So we have now your K equal to EA, 1 or L all over L squared. Let me just be just simply 1 all over L minus 1 all over L. Yes? So again, using the direct stiffness method, it's a very simple method. And what's the limitation here? The limitation here is that you must have a strain displacement function. Your strain displacement function, by the way, is dependent on your shape function, which will be dependent on your displacement function. So end of the day, you must have an assumed displacement function. So at the moment, what we did was just to use a linear displacement function, which is given by this one here. So take note, we started with this assumption. Can this be quadratic? Yes, if you want to, it can be quadratic. So by the way, to be able to solve for your displacement, we have now this one here. But what you see in your FE simulation is that you're able to get the stress. So how can we deduce the stress from all of these? How can we determine the stress? Take note that to be able to determine the stress, you must also have your shape function. How do we determine the stress? We have been using this finite element since last year. So we have been using that. We are able to determine the displacements. But the thing is that if you're using your ANSYS or Abacus, what you're determining in addition to the displacements are the stresses. So how can we calculate for the stress? We didn't talk this one. I mean, we didn't discuss this one during year 3. It's probably just a simple one, but we didn't discuss because it's not available in your notes then. So how do we determine the stress? So, of course, we know that your stress is equal to E multiplied by your strain. So, again, we're just looking at a simple bar here. Yes? So, that will be, say, dx, infinitesimal length. So there will be an infinitesimal displacement if we're going to apply a force and stretch it. There will be a infinitesimal displacement. So what will be your strain? What is your strain here? Du dx. It's that small elongation or that elongation divided by its original length. So we're not going to get the total length. We're just going to take the original length. Reason, we're assuming that this displacement is infinitesimal, very small. So we just need to have a representation. And this u here is a function of your shape functions. So that stress now is is equal to the modulus multiplied by your strain. But we were able to get expression of our strain as a function of u1, u2, and your shape function 1 and shape function 2, yes? So we have now this one to be n u1, change that, n1 u1 plus n2 u2. So we were able to get this one here. So n1 u1, n2 u2. So we were able to get that. So now we want to calculate the stress. We want to use this equation. So you substitute u here, so you have now this one here. Yeah? And you have down here du ddx of n1 u1 plus n2 u2. More? So we're not finished yet. Let's try to simplify this one. We have down here ddx n1 u1. Yes? So we can have this one to be ddx of n1 n2 and this will be u1 u2. So take the derivative of that, d n1 dx, d n2 dx. Yes? So these are your displacements, and then you can have now this one to be d1 d2, and this will be u1 u2. So you can have now this one to be your b transpose u. Yes? So take note, this one now is your d dx n1 u1 plus n2 u2. So we have now your stress to be equal to E d transpose multiplied by your displacements. So this will be u1 u2. So I'll just put there ui, meaning u1 u2. Okay? So now we are able to determine the displacements as well as the stress. Because that's what you see in your finite element model. You're not just limited to the displacement, you can also determine the stress. But from this hand calculation finite element, how do we solve for the stress? This is how you solve for the stress. But remember, this one is just for bar element. So we have a different equation, not really different, just a slight additional information if you're going to solve for your beam element. So it becomes more complex as we go to straight triangles, or you go to a quadrilateral element, which is basically the topic in your notes. Let's have an example. So you've seen this one already. We've done a lot of examples, but just to illustrate my point here, let's have a look at a two-element bar system. This one is element 1 and element 2. So we're going to determine, we want to determine the displacements and stress. Displacements and stresses along this bar here. So we know that the values here, your displacement here are 0. So what we want to know will be the stress along your first element and the stress acting on your second element. So we have now your stiffness matrix. We have derived this one. So you have K1 and K2. So you have now your area, modulus, and length given. So you will be able to determine the stiffness of each of the bar element. So you just add them to be able to get your global stiffness matrix, which is that, add them together, and that. Solve for your displacements and forces. So these are your forces and these are your displacement. But since this one and this one is equal to 0, or each equal to 0, then you can simply solve for your displacement at 2 to be PL divided by 3EA. So this, we have done this one already, and this one is one of the simplest problems that we have encountered. So just try to recall this solution. So with that, we are able to get this U2 at this location. We know that the displacements at 1 and 3 are equal to 0. So we can only get a numerical value for this one. So how do we solve for the stresses? Yes, so this should be B transpose. Sorry for that. So once you have the displacements, U1, U2, U3, you can now proceed to solve for your stress. But take note, you must have your strain displacement matrix. And how did we get that strain displacement matrix? We simply integrate the shape function with respect to x. So E here will be your Young's modulus. B here, we were able to derive this one already. And then you have U1 and U2. So solve for that. U1 displacement is equal to 0. U2 is solved using this one. You can now determine your stress for your first element. So the question is, will the stress be here or there? Neither. It's along the element. That's the limitation of finite element. So you're assuming that the stress along this element here is constant. And then of course you solve for your stress 2, which will be the stress along element 2. So again, just using that equation that we were able to get, B is this, U is that, and then you can solve for your stress. So you now have your displacement as well as your stress, which are the things that you can find from your finite element softwares. So all of these are in Moodle. I will be posting them. Okay, let's have a break and let's continue. After 10 minutes, we'll have more equations to come.